Hello everybody. So we are going to take tutorial for the first time. This is the tutorial 1. Our plan is like that. We'll have a total of 12 weeks for this course, and every week we'll be having one tutorial, approximately say 20 to 25 minutes roughly, and each tutorial will try to explain the basic concept. Basically we'll summarize whatever you have learned, and then we'll try to find out the insights in the material what we have started, and we'll do some tutorials, numerical problems, so that our concepts become clear. So the first tutorial goes like this. We'll cover the introduction to thermal and cold plasmas. We'll summarize what we have learned, the fourth state of matter, and then we'll do the process of ionization, recombination, diffusion and mobility, the basic processes that from this plasma. We'll summarize the concepts, and then thermal ionization and ionization equation, the plasma species distribution that plays a very important role. We'll do numericals on each of these topics, as well as at the beginning we'll summarize the concepts and the key points on each of these areas. So our tutorial begins. Plasma is called quasi-neutral. Gas is ionized, electrons are stripped off. Then they are special, and we call that as a fourth state of matter because they exhibit collective behavior due to long range electromagnetic interactions. And as we have told in our class that more than 99% of the universe is in plasma state, and the kind of state we see on earth, that is something very, very unusual in the universe. So this is, you just keep in mind when somebody asks you what is plasma. So just these 4 lines, if you remember, that can help you to tell what is plasma. Okay, so there is no ambiguity now. We move to the next one. As we have told in the name of the course itself, that this will address the theory and application in thermal and cold plasmas. So we are categorically excluding the fusion plasma because that is completely a different branch of plasma, that is way different from this thermal and cold plasma applications, cold thermal and cold plasma areas, because the kind of temperature there you will be handling is 1 million degree Kelvin kind of temperature, and the temperature that we will be handling in thermal cold plasmas, they are well below say 50,000 degree Kelvin for gas temperature, or even for electron temperature as well. So that is why we are confining to this thermal and cold plasmas. Basically you can call this as industrial plasmas. So again you would like to know what is thermal or cold plasma. So thermal plasmas, there all species are at similar temperatures, and when I say high, of course this is not million of degree Kelvin, it may be say 10,000, 20,000, 30,000 degree Kelvin. All species, irrespective of whether they are ions, they are atoms or they are electrons, they are at similar temperatures, and this high is with respect to our common experience of temperature that we can achieve in combustion, say around 600 degree, 800 degree centigrade. So with respect to that, when you are talking that thousands of degree Kelvin, like 10,000, 20,000, that is high, but it is no way high when you compare that with the millions of degree Kelvin that you observe in fusion plasma. And when you are talking about cold plasmas, there the electrons are hot. That may be 2 eV, 3 eV kind of thing. So that is 20,000, 30,000 degree Kelvin. But ions and neutrals are cold. They are so cold that you can touch it by hand. So it is, say, maybe well below 45 degrees centigrade kind of thing. So that is the interesting part. There are cases where the plasma you want to apply on biological substances where cells and tissues are involved, and they cannot bear a temperature more than 45 degrees centigrade. But electron temperature, that may be well high, maybe 30,000, 40,000 degree Kelvin, and that serves the purpose for which you are going to apply it. Then regarding the application areas, thermal plasmas we are using in welding. Then thermal plasmas we are using in fusion, but not for fusion reactions, but for material qualification, the kind of flux fluence that you require to validate a material or to qualify a material for a certain application, like the diverter region or so, we are using thermal plasma fluxes. So apart from that, in fusion kind of reactions, we are not going to the kind of thermal plasma we are talking here. So the temperature is well below, say, 20,000 or maybe 30,000 degree Kelvin at most. So we are working and we are roaming in that area, not in the million degree Kelvin. Then regarding the cold plasma, we are using in, as I told you, it is gas temperature is low, so we are using in medicine, agriculture, surface treatment, and all this. Now regarding the basic processes that forms the plasma, we can summarize like this. It involves ionization, atom lose the electrons to form ions, recombination, electrons recombine with ions and thereby they release energy. Then diffusion, because of the high gradient, pieces move from one place to another. So the normal convention of diffusion. So this gradient is gradient in concentration of the species. Whenever that is there, they will try to equilibrate. So from high concentration, the particles will try to move to the lower concentration area. Then mobility, this plasma is formed usually in electrical discharge, so electric field is involved. Then charged particles movement in an electric field is basically controlled by mobility. So these are the basic plasma processes: ionization, recombination, diffusion, and mobility. So just if you keep these ideas in your mind, then you will be able to say what is plasma and how that is formed through the basic plasma processes. Then what we described and we derived rather in our classes are the thermal ionization and the Saha ionization equation that helps in understanding that. So the thermal ionization and Saha equation basically describes the degree of ionization in thermal equilibrium. It depends on temperature, electron density, and ionization energy, of course. And Saha equation tells that very nicely that Ne Ni by N naught. Actually, this is a generic type of equation. So if you put R equal to 0, then that is neutral. Then this becomes N1. So that is the first ionized state. Then this is electron. And on the right side, this Z represents the partition function. T is temperature. E ion is the ionization energy. So this is a generic equation. So if you want to go for the first ionized state, you just put R equal to 1. Then this will be N1. So this is the N2 will be the concentration of the second ionized state. This will be the concentration of first ionized state. This anyway will be electron, and this ion will be the second ionization energy. So this way, you can find the species distribution in plasma. So they equally apply in all plasma areas. Now, plasma species distribution is another important thing. So, what are the species that plasma can contain? So, plasma contains electrons, ions, neutrals, and photons. So, I am just summarizing what you have learned in your classes, that you will be dealing with electrons, ions, neutrals, and photons. So, in the neutral particles, you include the atoms as well as molecules. Okay. So, because sometimes you will be using molecular gases like nitrogen, oxygen, and there at even at pretty high temperature, some percent of molecule may exist. So, the plasma, when it is you can call it plasma, that may contain some part which constitutes of molecules. Now, species distribution depends on the kind of energy that you have imparted in that. So, depending on that, their velocity, then the species concentration will vary, and depending on the pressure, the collisions will be decided, and that again will alter the species distribution. So, depending on pressure, the kind of energy input, your species distribution will be fixed. Cold plasmas are often exhibit non-Maxwellian kind of distribution, but thermal plasma you can very well describe using Maxwellian distribution. Now, metastables and excited species, they contribute to the chemical reactivity. I have told repeatedly that these metastables and this excited species can make the reactions to happen at a much faster rate. So, this is regarding the species distribution. So, what you have done, you have understood what is plasma, you have understood how we can form the plasma through basic processes. Now, you know the species has been formed and what may be the form of distribution and what may be the constituent of the plasma. So, once you know that, then we start our numericals. So, the first numerical that we like to handle is the at a UV light photon of wavelength 290 nanometer. Okay. So, you know that strikes an electron. 290 means it is UV and an electron in a hydrogen atom. Okay. Hydrogen atom you are very much familiar, one proton, one electron, and it is in ground state. The question is, what will happen to that? Whether the atom will be ionized or not, and what will happen if the light continues to fall on a large collection of atoms. This is quite interesting that I have a UV photon that is coming, whether it will be able to ionize the hydrogen atom. Let us see. When the energy, what is the photon is having here, it is equal to Hc by lambda. Then if you use this lambda, then you can do the calculation on your own and you will find that it is 4 eV. So, if you want to convert it into eV, you need to divide appropriately by 1.6 into 10 to the minus 19, so that the results come in eV. Okay. This H is of the order of 10 to the minus 34 in MKS units, is 3 into 10 to the power 8 meter per second, and lambda whatever you have given in meter. So, if you put that, that will be coming in joule. Then you divide that by 1.6 into the minus 19, then only you will be able to get the this energy in electron volt. Now, what we have got is that 4 electron volt, and we all know that ionization potential of hydrogen is 13.56 eV. So, if a single atom is there, the atom is in ground state and the atom is saying that I need 13.56 eV to get ionized, and you are supplying through photon only 4 eV. So, that will not help. So, the ion will not get ionized, nothing will happen. So, that is the case 1. Now, case 2, you have a large collection of atoms. So, what is happening? They are now form a distribution through collisions depending on the kind of temperature, and what you are seeing here is that I have plotted the Maxwellian distribution as a function of, at different temperature, as a function of speed. What you are seeing here, that the number of particles with certain speed is decreasing. Maximum number of particles what you are getting over here, the peak is reducing. But at the same time, you know that the area under the curve of this tell you what is the total number of particles in your system. So if that is the case, as you go to higher temperature, you are seeing that more and more number of particles are moving towards the higher velocity zone. And this is called the Boltzmann tail. This asymptotically reaches the zero value, and in the tail region there may be certain particles which are already having very high energy. When they collide with some other molecules, hydrogen atoms, then they will excite them to appreciably high energy state, and they, from that state, if it receives a photon of say 4 eV, it may be sufficient to just make it ionized. So what is now you are getting, when you are getting an assembly of large collection of atoms, then they may collide with each other, because that is unavoidable. At any temperature collision will happen, and some of the particles may have very high energy, and they will assist the atom which is in ground state to reach an excited state. And in that excited state, if it receives a photon of say 4 eV, that UV photon which has come, it can ionize it. So it is possible that you will get a good amount of ionization if such UV light falls on an assembly of this large assembly of these atoms. So this gives a very, very fundamental insight that to generate plasma, an assembly, a collection of particles may help, because of the very, very nature of the Maxwellian distribution, or any whatever energy distribution you take, natural energy distribution kind of thing, you may get some particle which are always having very high energy, and they may excite the atoms in ground state to a pretty excited state. If the atom in excited state receives a photon of this kind, that can ionize. So that is the way you can get a pretty good amount of ionization. And if you are assisting that through some application of electric field, that may cause breakdown as well. So this is a fundamental process which should be kept in mind while you are analyzing the other effects. So now in a numerical 2, here what we are doing, we are trying to go for nuclear fusion. Okay. So there, just we want to know what kind of temperature that is required over there. And we know that it is around 0.25 MeV. It is a typical order that we talk about. And on the right side, this is actually a sun. This actually I caught in my mobile camera. And you will be surprised to see that the camera is so powerful, the mobile camera itself, that you are able to grab the solar flares. You see the tiny, tiny spots that is coming out. It is very surprising that a mobile camera can capture those things. Now, this is a fusion plasma which is gifted by nature, by which our earth or the universe runs. Now, this one is man-made. This is a tokamak. I have just made a cartoon of that, and you see that the plasma millions of degree Kelvin temperature, and you are confining that within the device, and you will notice that this plasma is not touching the wall, neither the inner wall that is there, and you are keeping that in the space in between the inner and outer walls, so that the structural integrity is maintained. And you see the spiral kind of thing, because that is a toroidal and poloidal magnetic field, you are forcing the charged particles to rotate in this helical path. So I tried to show that in showing some spirals, assuming that they will follow these spirals and make more ionization over there, and they will make that those regions emit higher. So you may get a this kind of visualization, but this is an artist's picture, artist's impression. This is not the actual one, because it is very difficult to open the tokamak. This is a tokamak device and look inside actually. So that is not possible. So whatever you are seeing is an artist impression, and it is supposed to be like that, you know. So just to estimate in this case only, for atoms in thermal plasma, the average kinetic energy of the order of eV, that you know. So to estimate the temperature for fusion plasma, we know that suppose DT reaction is a common reaction that is in that is targeted in fusion reactors. So D and T, they both of them have only one electrons over here, and you need to bring them close enough so that they fall in the nuclear range. That is this 10 to the minus 14 meter. That is you know, the femtometer scale. So when you put this in this nuclear interaction range, then they fuse together, and from the fusion. So here the kind of Coulomb barrier you can easily find out. This is the Coulomb's law, and that should be of the order of kT. And I request you to do this calculation with this R 10 minus 14 meter, and you know the electronic charge, you know the Boltzmann constant. So T you can find, and it will be easily found that it is of the order 10 to the power 9 Kelvin. So this is the temperature that you require in fusion plasma as a fundamental basic requirement. So you are getting that from the directly from the, you know, crossing the Coulomb barrier in the nuclear force range. Now you know the thermal plasma, what may be the temperature? It is around say 1 eV, 2 eV kind of thing. So it is 10. So now compare this 11,000 to 10 to the power 9 Kelvin. So then you just make the distinct difference between these two regime. One is fusion and one is your thermal and cold plasma regime. In cold plasma, the heavy species temperature is say around 300 Kelvin only, okay, and not even anywhere in 1000. This what you are seeing here, this may be in thermal plasma, gas temperature, or it may be electron temperature in cold plasma. So now you are clear about the temperature, how they appears, and from basic calculation, basic criteria, you are seeing that you require a temperature of 10 to the power 9 Kelvin. Okay, so that is the thing, and this is the last one in this tutorial that I will tell you, that in a photoelectric experiment it has been found that tungsten metal has a threshold wavelength of 2100 angstrom, and from this I just want to know what is the work function of the material. So this is a very easy way out to find work function of material, okay, and whenever the electrons come out, then you can collect it and concentrate a current, and which you can detect using a current meter. So here what you are seeing, that the work function, if you note this lambda, that is coming to be 5.4 eV. So h is Planck's constant, c is speed of light, and lambda is the wavelength that you are noting here, which wavelength you have allowed to fall on the material. Then you see that the work function comes to be 5.4 eV. Now you know that this tungsten, for which we have calculated this one, is a very common material used as cathode in plasma devices. Like this one I have shown in your classes, that this electrode, this cathode emits electron made of tungsten. Why? Because it is having a very good thermal conductivity, electrical conductivity, and emission properties. And emission properties comes from the work function. And here what you are seeing, it is quite large actually, 5.4 eV. It's not a good enough. And what I do in this, actually, in this I list some of the typical cathode materials which are used in common use as common electrode materials. So if you go through, you see that cesium, potassium, sodium, calcium, they are having pretty low work function. So we are very much interested in that, because if they are having so low work function, they will be able to easily emit the electrons. But they are other mechanical properties like melting point, structural rigidity, electrical, thermal conductivity doesn't make them many times not suitable for a specific application. So what we require, a very hard material, structurally strong material, which will have very low work function, which will have very good thermal conductivity, which will have very good electrical conductivity. So they suits our application. So you see that tungsten, as I told you, it is having a this work function. What we found here, it is 5.4 eV. So it goes like this. Now when you thoriate it, just like 2% thoriated tungsten, that is a common commercial electrode material, the work function reduces to 2.6 to 2.7 electron volt. Now you see that it is very much comparable with the very low work function material, but just putting an impurity of 2% thorium oxide, you are able to bring down the work function to 2.6 to 2.7 electron volt, but at the same time you are retaining all the thermal and mechanical properties. So 2% thoriated tungsten is a very common electrode material where oxidation is not a problem. So for non-oxidizing gases, 2% thoriated tungsten material is a very ideal electrode. But when oxidizing gases are there, this green zone, what you are seeing here, this is 3.9 and this is 4.1, this hafnium and zirconium. So hafnium obviously is a better material and zirconium is close to that. So this oxygen cutting torches, as I have told in the classes, and you will be seeing in the later classes, that hafnium is used in oxygen cutting torches as cathode, and similarly for air plasma devices where oxygen is present. But tungsten cannot be used there, because tungsten forms tungsten oxide, and tungsten oxide is having a very low melting point. So these are the kind of work function that you are here, and here what you are seeing, that 4.5 to 4.6 EV is the work function for this tungsten. And in this problem, just from elementary calculation, we have got 5.4 EV. So this is very close to 4.6 or 4.5. So the little bit of error that you find in your theoretical estimate, your experimental estimation and theoretical values are always there. And in this tutorial also you are finding that there is a little mismatch, and this kind of little mismatch will always be there when you go for the experiment and when you go for the theory. And you should be actually well prepared mentally that these are going to happen in most of the experiments and theory. There will be some mismatch, and it is your duty to explain where from the mismatch comes, how whether it is a theoretical approximation is causing that thing, or there is some error involved in the measurement which is causing the mismatch. So I just wanted to highlight that, just because of the small difference between the experiment that I have proposed in the previous numerical and the theoretical value that has been listed in literature. So there is a variation, of course, 4.5 to 4.6. Similarly, you see that thoriated tungsten is also variation, and say graphite is also having some variation. So this depends on the kind of material and the impurities that is involved there. So these are things. So I stop this tutorial here. I hope that you have enjoyed this tutorial. We will meet you in the next tutorial in the next week. Okay, thank you.